Hello! In this video, we are going to prove the following lemma. Let A, B, C, and D be objects. Then the ordered pair A, B is equal to the ordered pair C, D, if and only if both A is equal to C and B is equal to D. Okay, now our definition of an ordered pair goes like this. Right, given two objects, X and Y, the ordered pair X, Y is really the pair set of two sets. One of those sets is the singleton set of X, and the other set is the pair set of X and Y. Right? So this is the definition we're going to take for an ordered pair. Okay, but that leaves us with a question of, well, what do we mean by singleton set? And what do we mean by pair set? Well, here's what we mean by singleton set. Given an object X, there is a set which we call the singleton set of X, which satisfies the statement that for all objects T, T is an element of the singleton set of X, if and only if T is equal to X. And also, what do we mean by pair set of X and Y? Well, here's what we mean. Given two objects X and Y, there is a set called the pair set of X and Y, which satisfies the following statement. For all objects T, T is an element of the pair set of X and Y, if and only if either T is equal to X or T is equal to Y. Right, so that's really what these two sets mean. Now, there are two facts regarding pair sets that we're going to rely on. It's under the condition that we have two pair sets, A, B, and C, D, which are equal to each other. Here's what the two facts are. A is equal to C if and only if B is equal to D, and A is equal to D if and only if B is equal to C. So now let's get into proving the main result. To start out our proof, let's give ourselves four objects, A, B, C, and D. And our goal is to prove this is true if and only if both of these things are true. And since we're trying to prove a statement containing if and only if, what we're going to do is we're going to prove if this is true, then this is true, and then we're going to prove if this is true, then this is true. Let's start by proving if this is true, then this is true. And to do that, suppose A, B is equal to C, D. Now, what is A, B? It's precisely this, where we replace X with A and Y with B. And similarly, C, D is precisely this, where we replace X with C and Y with D. And since the ordered pairs are equal, well, that means that these two sets are equal. Okay, now we know that the singleton set of A is an element of the ordered pair A, B. Right? This comes from the definition of a pair set. So, since this set is equal to this set, the singleton set of A must be an element of this set. And again, by the definition of a pair set, the singleton set of A must be equal to either this guy or this guy. And so what we're going to do is we're going to prove in either case, we have that both A is equal to C and B is equal to D. Let's start with case one, where this is true. Well, by definition of a singleton set, we know that A is an element of the singleton set of A. And since these two sets are equal, this means that A must then be an element of the singleton set of C. And by the definition of a singleton set, A must then be equal to C. So we've proven that A is equal to C. All that's left to show now is that B is equal to D. And to say that B is equal to D, notice that these two pair sets are equal. And based on what we have here, these two parts of the pair sets are equal. So we can apply part one of our lemma. Applying part one to our lemma, we obtain that because these two are equal, that these two must be equal. But now, we can apply part one of our lemma again, right? We see that we have two pair sets that are equal, but based on what we have here, these two parts of our pair set are equal. So these two must be equal. So we have shown that A is equal to C and B is equal to D, which is exactly what we wanted to show. So that completes case one. Now we're going to move on to case two, where this is the case. Now, by definition of a pair set, we know that C is an element of this set and D is an element of this set. And since C comma D is equal to the singleton set of A, it follows that C is an element of the singleton set of A and D is an element of the singleton set of A. And by definition of a singleton set, we have that C is equal to A and D is equal to A. So we have that A is equal to C, so all that's left to show now is that B is equal to D. And to see why that's the case, well, again, let's apply our lemma. We know that these two pair sets are equal, but based on what we have here, these two parts of our pair set are equal. So if we apply part two of our lemma, because these two parts of our pair set are equal, these two parts of our pair set must also be equal. And now, performing a similar argument to what we just did, we know that by definition of a pair set, B is an element of this pair set. And since this set is equal to the singleton set of C, B must then be an element of the singleton set of C. And by definition of a singleton set, B is equal to C. So what do we have here? Well, B is equal to C, which is equal to A, which is equal to D. So B is equal to D. So we have proven that in this case, we have that A is equal to C and B is equal to D. So we have proven both things. So putting this together, we have that in either case, both these things are true. So when we consider that either this is true or this is true, well, no matter which one of those happens to be the case, we have that both A is equal to C and B is equal to D. So we have proven if this is true, then both these things are true. So that proves the forward. Now let's prove the converse. Now to prove the converse, we're trying to prove if both these things are true, then this is true. So let's suppose that both these things are true. Our goal is to prove the ordered pair A comma B is equal to the ordered pair C comma D. Well, really, to prove that, it's just going to rely on properties of equality, right? Since A is equal to C, we can replace the A here with C. And since B is equal to D, we can replace the B here with D. So the ordered pair A comma B is equal to the ordered pair C comma D. Right? And that's exactly what we wanted to prove. So that completes the proof of if these two things are true, then this is true. And we've proven both directions of the if and only if, which means we've proven the entire statement. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.